don't show the complete file?
Well, I wish I don't have that, but let me work on that for the next Haskell Symposium. So I'm going to. The topic of this talk is resource management. We're going to look at different ways to manage resources in Haskell. And the kind of resources I have in mind are things like file handles. So as you know, for files, to access a file in those programming languages, you have to first open it, and then it becomes accessible, so we can access the file through the file handle 0 or more times. And finally, we're supposed to close the file handle. So the kind of properties that we want to ensure, either by dynamic checking or static checking or combination of both, is that first, after you close the file handle, you don't try to say read or write the file again. And we would like to minimize the amount of runtime checking that we have to perform to achieve that. Another thing we want is to close the file handle as early as possible, ideally right when we don't need to access the file anymore. So this is what we call a timely disposal, which is important for scarce resources, unlike memory on your typical laptop, which has a lot of so where you can expect the garbage collector to come in a little bit later to collect memory if necessary. And finally, because we're performing I/O, and I/O is fraught with risk of error, we want to have our approach be compatible with error handling. Okay, so for this talk, I'm going to use a motivating example that's inspired by real-life applications. That is the following access pattern of files. So suppose we have two files, input to the left and config to the right. I've grayed these files out because we have yet to open them. And we want to do the following. We want to open the two files, and we want to find in the first line of the configuration file some output file name. So this is telling us, imagine you're writing a web server in Haskell where the configuration file contains the name of the log file. So then we create a log file, or we'll open it for writing, and we're supposed to say zip the input file and the config file into the log file. Okay? Just to use both the input and the configuration to produce some output to a new file named in the config file. And then now that we have reached the end of the config file, and the web server is up and running, say, we can close the config file and keep using the input file and the log file we just created for them to copy the rest of the input file to the log file. Okay? So we're going to look at different ways to program this kind of example in a series of approaches to this topic. Oh yeah, I just want to stress, this is the last point, was just at the end, of course, we want to make sure that all the files are closed. So again, the goal is to manage resources such as file handles in a way that ensures both that the resources are not accessed after closing, and also that they're disposed timely. And the solution, the main solution we propose in the paper, is that of nested regions. So we're going to start with using functions like Haskell's functional state threads to ensure that, in some sense, file handles don't leak beyond the computation where they're supposed to be used. And then we're going to enable more timely disposal of resources by nesting these regions encoded as monadic transformers and using some technical tricks to encode implicit region subtyping so that you can use file handles that live in one region while computing another region. So one way to understand this work is that we're taking some native associated capabilities, such as file I/O in Haskell, and which may not be safe a priori, but we want to impose some kind of syntactic discipline, in other words, types, on these capabilities to make it safer. Okay, so this is a bit different from, for example, I think 2 days ago, we heard about a translation of capabilities into a functional language. There we're sort of implementing a capability system, whereas here we're making use of existing native access to resources. Okay. Now, again, the resources we're being interested in are kind of like file handles, but there are other kinds of resources as well. For example, database connections, OpenGL context, things like that. And the subtyping facility that we use can also be used for things like automatic differentiation, other places where you want notions of subtyping. And at the end, if I have time, I'll get to another approach which we recommend less for general use, and that is to perform manual resource management, but then use type-level tracking to ensure that the manual closing, for example, of files is safe. Okay. So the outline of this, the rest of this talk is very simple. I'm just going to go through a bunch of approaches, and for each one tell you how to use it and how to build it. Okay. So let's start with some existing Haskell library functions. In particular, WizFile. WizFile is supposed to help us ensure that, well, when we open a file, we always close it and we only use the file while it is open. Right, so here's how we use WizFile. We pass it the file name you want to open, this is what you want to read or write. And this sort of body of the WizFile, this, how should I put it, the callback. And the idea of WizFile is that it's going to open the file, pass, if the open is successful, the resulting handle to this body, and then when the body finishes, either successfully or with an exception, make sure the file is closed. Okay. So that sounds good. This is the documentation from the documentation for the function from the library. But note that the type handle here could actually be the same as this A, which is the type that's actually returned, okay, from the enclosed computation. So we could write some code like this, where we open a file for reading, and then the computation we perform on the resulting handle is just to return it. And so what it's going to do is going to open the file, produce the file handle, make sure it's closed, that's the job of this file, and then read from it. Okay, so we're going to be reading from an open file, and that's bad. So to prevent problems like this, the insight, something new, is that we could try to somehow prevent this type handle here from unifying this type variable A. Okay? And to do that, we can draw an analogy to state threads, where the goal is to make sure that mutable cells allocated inside a stateful computation do not leak out of the computation. So here we want to make sure that file handles open as part of computation do not leak out of the computation. Okay? So just to remind you what state threads are, in the Haskell ST library, we define two type constructors, ST and STREF. The idea is that ST is a type of stateful computations, and STREF is the type of the mutable cells used in stateful computations. And here's how you allocate a new reference cell. You give the initial contents the value A, and then we have a monadic computation that produces value, which is a mutable cell reference. Okay. And to access it, given a reference cell, we can either read from it or write a new value into it. Okay. And the key to making sure that these accesses are safe is that there is a type argument, usually written S, that passes both the ST constructor and the STREF constructor, so that, for example, when you allocate a reference cell, the computation which you're doing the allocation is somehow linked to the reference cell that's allocated. And you can only read a cell or write to a cell in the same computation. Okay, so again, notice this is the same S here as is here. S is known as function type because it has no runtime representation. And note that this facility of mutable cells don't give you any way to explicitly deallocate mutable cells. The idea is that at the end of the stateful computation, when we're sure that we don't need any mutable cell anymore, we can deallocate them all at once. Throw the whole thing away. And to make sure that we don't need those cells anymore, we use this universal quantification and to harmonize it in the type round ST to enclose the top level computation so that, well, for example, if there's any STREF that this computation is trying to return, it won't be able to unify with the A. Okay, so I hope this is familiar to most of you. Now we're just going to draw an analogy between this use of this way to protect state, way to perform safe I/O. We define a type SIO of safe I/O operations, just like ST before, and we define a type constructor S handle, which is the type of safe handles, kind of like the reference cells that we had before. And again, we have ways to allocate and access these resources, namely file handles. And again, when we allocate these resources, we use this Hansen type S to link the computation with the resource so that we can only use the resource in the computation that's supposed to be used in. And finally, we can encapsulate the computation, the safe I/O computation, using run SIO at the top level. And the idea is that we can apply run SIO to something that performs some safe I/O. The result is a usual I/O action, which is guaranteed, therefore, to always close all the files and never access the files after they're closed. Again, there's no facility for closing the file explicitly because all the files get closed at once at the end of the run SIO computation. So far, so good. So here's how you use it. Pretty much you're just writing usual monadic code, except with just this additional safety guarantee. So this is an example from before, and here is the main program for implementing this example. I just want to point out some features. First of all, there's wrong SSIO at the top. So you encode the computation inside wrong SIO, just like you encode the stateful computation inside wrong ST. We are able to define monadic combinator, so you probably already have used a high-order combinator inside TIL, which is a looping combinator. You continue to use that here, because this is just monadic programming. Finally, you can put some sub-part of the computation. For example, here we put the sub-part of the computation related to the config file in a separately compiled function. So test internal is implemented here. It just performs some other task, okay, which is invoked from the main program. So this is just how you will write a usual monadic program that performs file I/O. Instead, we use types to ensure that the file handles are recapped. Okay, so what I want to visualize this computation is that we have this sort of box that contains the monadic computation. And inside the box, I want you to read the lifetime of the file handles from top to bottom, so that the time flows from top to bottom. So you can just open a bunch of file handles inside the box, but we know that these file handles will not be used outside the box, so we can close them when the computation ends. And let me just sort of make a side comment about error handling. We can just use the usual facility exception handling for handling errors in the system. Again, just as if we were writing usual monadic I/O code. One detail is that we want to guard against people using exceptions to sneak non-safe handles out of the computation. So exceptions are sanitized to remove the low-level unsafe handles contained inside before they're passed outside the safe I/O computation. All right. So a word about how to implement this. Basically, we want to use the same representation of handles at runtime as before. But we want to keep track of, at runtime, one piece of dynamic information, which is the list of open handles. Okay, so we have an I/O reference cell that's allocated at the top level, which contains initially the empty list. And every time we open the file successfully, we stick the resulting new handle into this list. And at the end of the computation, whether it's successful or it's sort of an uncalled exception, we try to close all these files up. Okay. And so this list of open handles does impose a runtime overhead. But I want to contrast that with the runtime overhead that's currently imposed by the unsafe I/O system in the Haskell library, which under this scheme will no longer need to be imposed. And that is that we need to check in current Haskell I/O at every time we access a resource, whether it's open. Right? So when we read from a file, the handle actually has to say, am I open? Whereas once we have this type safety, we don't need to track that anymore. We just need to track the list of current open handles. And every time someone tries to read or write a file, we know it's going to be open, so there's no need to check. Okay. So we only have the overhead when we open the file, but we don't have the overhead at every access. Okay. Just a little bit more about how to implement this. As you know, there's a monad I/O type class in the Haskell libraries for monads into which I/O computations can be lifted. So we have sort of a private version of that. It's private because we don't want people to randomly lift I/O, especially file accessing I/O computations into our safe I/O monad. But basically, it's the same. So we have a monad class that supports lifting of I/O operations, brace, which is like bracket, and snap, which is like cache. And I/O itself is a monad that supports this, and we lift it over a reader monad transformer, which is a reader monad transformer that provides this I/O ref to the list of open handles. And we want to keep this name unexported, these names unexported, from the safe I/O library so that clients cannot define new unsafe instances of this class. So these unexported names protect our library, and the library forms kind of a security kernel against attacks from what they call adversarial programs. So now that's a basic idea, and so the point so far is that we want to prevent handles from leaking, just like we want to prevent other kinds of memory resources from leaking. But there's a problem with what we've done so far, which is that config, the file, is closed too late. Remember that we can really already close the config file once we're done filling the config with input. But in the picture that I presented earlier, config is actually open, it's closed only at the very end of the computation. So we really want to close config earlier. So the idea to doing that is to create a nested sub-computation in which config can live. Open config inside and access it inside. And we're going to distinguish the handle config, which lives inside the sort of nested computation from handles outside by using a different phantom type S inside the nested region from the parent region. So of course we want to make this facility makes us certain that we won't try to use config like here where it's closed. Okay? Because then the type S inside will match type R outside. But that also, this type mismatch prevents us from zipping input and config into R. Because at this point in the computation, we want to use not just config but also input and log. We want to use all three files at once. So even though we don't want to use child handles in parent computations, we do want to use parent handles in child computations. To achieve that, we can, and this is an idea that Bouncing Savage actually proposed just for state, we can have a additional primitive which allows us to import some handle from the parent and treat it as if it were a handle that belongs to the child computation. So we can change the representation of regions so the phantom type actually has kind of structure that tells us about this sort of ancestry relation between these computations, these nested computations. But that's a bit inconvenient because you sometimes don't really care whether one region, region A, say, is the parent or grandparent of another region. All we care about is that one region is an ancestor of another region. So for example, if I write some code to copy lines from one file to another, then we really only care that the computation in which I'm doing the copying is a descendant of the handles, the two handles. But I don't really care whether one handle is in the region that's a parent of another or a grandchild of the other handle's region. To enforce this to make it easier to implement this kind of region polymorphism, Field and Morissette proposed that we make as a central part of our sub-regioning system these things which are subtyping witnesses for region subtyping. So let me first explain that subregion RS is a piece of evidence that says whenever you have some computation that can be performed in the parent region R, I can perform it in subregion S. So S could be the same region, or it could be some child or grandchild region. And when we create a new region, instead of creating a computation where the phantom type is a tuple, we just pass the subregion witness, so that we can then import any computation you could have done in the parent region into the child. And by composing these functions, we can import grandparent region computations into some grandchild computations. So all we need to ensure that config is closed early is to add this single primitive to our library. And this primitive can be used like this. So I've changed the code from earlier for the same example. So the basic change is that we use new region to put the part of the region that involves config into a child computation. And this child computation receives this subtyping witness, which can be used in two ways. First, when we want to open a handle during the child computation, such that the handle nevertheless lives and will be disposed along with the parent region. Okay, so we're lifting the creation of a handle from the parent region into the child computation. We also need to use this lifting when we want to access these handles that live in ancestor regions. So when we want to access the input file or the log file, we need to use lift and SIO. though if we want to access the config file, we don't use lift at all because that file actually does live in the child. Okay, so if you write this code, then Haskell actually automatically infers this nice type for test internal. But you have to juggle these with region subtype witnesses. So for the remainder of my time, I'm going to just briefly talk about how to not have to pass these explicit subtype witnesses around. Okay. There's something about implementation, but it's basically, there's nothing that happens at the, okay. Yeah, just okay. So, as I said, we want to not write these lift SIO, these subtyping witnesses. So what I'm going to show you is how to avoid writing calls or, to lift SIO, except when we want to open a handle in the parent region during the child computation. Okay. So the basic idea is to note that these subtyping witnesses look very much like they are monad morphisms. They are morphisms from the parent computation monad to the child computation monad. Okay. So this inspires us to simply represent the child region by applying the monad transformer to the parent region's computation. So we already actually done it once. We started with an unsafe IO monad, and we applied a essentially reader monad transformer. We applied this monad transformer to get our first safe IO monad, but we can keep doing that. We can apply the same transformer, IORT, the transformer that got us from unsafe IO to safe IO, and we'll do it again to get a child, safer IO monad from the already safe IO monad. Okay, so this gives us a family of safe IO monads, which is generated by these two instances. Okay, and we can still lift computations from a parent region R to any child. Okay, so now to represent child computations, we apply this monad transformer to the monad for the parent region. Okay. Another ingredient of the system is we want to automatically detect whether one region is an ancestor of another. And so for that, we define a monad race predicate, which is true just in case M is the ancestor of M. Okay, so M is the ancestor of M, M's ancestor is children, its grandchildren, and so on. Okay? And that allows us to revise the API of the library. So for example, if you want to read a line, as long as the handle is in the region that's an ancestor of the current computation monad, you can do it. Right? So as long as M is the ancestor of N, you can read from handle M to get the answer. Okay, and so on and so forth. Now we can write the copy program that I mentioned earlier, and we'll have this type. So basically, if you have two regions, M1 and M2, each of which is the ancestor of the current region N, then you can copy a line from a handle in M1 to a handle in M2 inside the computation in monad N. Okay. And we can also, coming back to the earlier motivation, omit all the mentions of lift SIO except when we're creating a parent handle in child computation. Okay. And the type is conferred. The implementation is actually very simple. New regions actually just run SIO. Right? To spawn a new computation, you can do it either at the top level or inside another nested computation. And to lift a computation from a parent region to a child region is just to lift the computation it's just lifting for the reader monad transform. So that's why there's a constant. Okay. And the only bit of type trickery is how to implement monad race for detecting region ancestry. And I just flash this slide by you, and you don't have to understand it. Well, if you don't like that, you can always just write these instances. That's fine too. There's no principal reason you have to go through all this. Anyway, so just to recap. The first idea we had was that regions can be used to encapsulate not just memory access, but other kinds of resource access. And we can represent nested computations using monad transformers. And finally, this slide that just flashed by you gives us a practical trade-off between, on one hand, the convenience of implicit subtyping, and on the other hand, the convenience of type inference. Okay. I think I just finished now. Let me just mention that, anyway, there's no type trade-off. Okay. So I only have time to tell you about one of the 2 ways to manage scarce resources when you provide static guarantees in particular, not just that resources are accessed safely, but also that it's also in a timely way. And it's also compatible with all the other things we like to program in Haskell. Thank you.
So we have time for 1 or 2 quick questions. Ralph.
You made both claims about the safety. How do you actually prove it?
No, this is a quick answer.
How do you prove it?
Oh, no, meaning no, we don't prove it. So how do we not prove it? Oh, well, the first attempt will be to follow the parametricity space proof which is not totally valid.
Seek and search for all these nice little additions to Haskell.
Well,
seek is a node as it stands in Haskell.
Right.
I don't think seek is a problem here, Ralph. This particular problem.
I want to see proof.
But so do we.
Please let us know when you're able. Please let us know when you have to do it.
Just like that
Maybe just a comment. Maybe just a comment to Rob's question. So yes, parametricity is, as originally there might be some questions, but then Amr and Monchieh's paper in this extended abstract. They showed how to, the approach to proof in Haskell. So essentially you create the typed interpreter, and then you say the typed interpreter is faithful to the untyped interpreter, and then it's a progress theory. So we can use exactly the same because our techniques, and even they, in their paper, they consider lazy regions, so they consider nestings, and they consider, a nested region. So we can use their techniques. So we know that the proof methods, we haven't performed them, but there are good proof methods. So we can use what Amr and Monchieh did in their paper. And they don't use parametricity, so they do it all weight-based way, and I think it's a serious proof. And the second, because we implement essentially the calculus F region by Fluid and Morrison, we can refer to their result because our implementation is the faithful implementation of the calculus. And they prove the sound of theory for it. And the computation and the proof icon, so actually they were again parametricity as a whole. So they have the proof for their case.
Okay, let's thank Ken again for his great talk.